Okay, welcome back. For me, it's been a while. This is actually the first lecture I'm recording for this semester. The other ones have been recorded last semester, so hopefully they're still good. And I need to kind of stretch and remember what it's like. But anyways, so um, last time, if I remember correctly, we were talking about where are we at? Bellman equations, right? So the Bellman equation, also what's known as the Bellman backup, is sort of this idea that we essentially can, given that we know the model of the world and we have a given policy, we can essentially model what our value is based on this sort of like recursive calling of the value function or the state action function over and over and over again. So you can kind of imagine having a state, and you know which state you may be in, and then you know the values of those states based on the same equation, and then you kind of recursively call this over and over again. Again, this was named after Richard Bellman, who was sort of the pioneer of dynamic programming. If you've done anything like A star or any kind of you know uh, thing like that, this is the same kind of idea. So this is not like a new idea, but for reinforcement learning, given a sort of Markovian like an MDP, a Markovian decision process, we are able to apply these ideas to essentially then determine the value of any given state in our system. And if we know the value of any given state in our system, then we know what the optimal sort of path to go through is. So once we know this, once we can evaluate these values and then we can essentially just turn our reinforcement learning problem into a decision-making problem. And when you have uncertainty, such as a stochastic process or a stochastic world model, right? I mean to go left and I end up going right. What we're doing is we're essentially taking the expected value of our things. So kind of like to formalize this, let's talk a little bit about this in the context of dynamic programming approaches from reinforcement learning. For this week, we're going to have a number of different shorter lectures that cover different approaches to reinforcement learning. We're not going to touch on too much deep learning stuff, although it will come up here and there, and I'll kind of point out where you'll see it, especially in the not necessarily in the context of dynamic programming, but other things. And and so this week is going to be really about sort of a variety of different techniques and strategies, and I think kind of the core of RL, as we'll see how we can start to solve these problems with world models, without world models, with different kinds of parameters. So let's dive in. So to kind of review, right, we have an MDP. An MDP, you have an agent inside of an environment. You start off, you're given an initial state. The agent has to then make a decision of what action to take. That action is then transferred to the environment, and in return, the environment returns a reward signal of some kind and a new state, or a termination of that if we're in an episodic context, right? So if we know the environment model, meaning we know that given a particular state, right, the likelihood of transitioning to a different state, if we know those transition probabilities, right, we can just apply this and just literally plug in those Bellman equations as we've been talking about. And we're based in the context of the Markovian assumption being that the probability of the next state is the same regardless of the states that came before our current state. In other words, the past doesn't matter, only the future matters. And so in this context, right, dynamic programming allows us to essentially evaluate these equations down in the bottom left, right, where if we're in a particular state, our value of a new state is going to be the maximum of our Q function value, meaning if I'm in a current state and I take the action with the maximum Q value, right, then that's going to be the value of being in the current state, because it's essentially just evaluating that Bellman equation, as you can see below. And if we plug that in, right, into this optimal value function, you can see that we're just taking the maximum action against the future expected values given this transition set of probabilities. And this is all for optimality. So this is actually, if we know all of this, if we know the model, we don't actually even have to think about a policy where we can just sort of directly evaluate these things, as you can kind of see here, right? It's sort of this self-fulfilling set of equations. And this math may look kind of like what's the deal, but this math just literally just pops out of the definitions of the value function and of the Bellman equations that we talked about in the optimal case. So as much this is I think something that always kind of gets me off a little bit, like what's going on, but this is in the case of optimality, and that means that we know all of these values. However, in reality, we generally do not know them, right? So how can we approach this given that we don't know necessarily all of these values? And I see I'm kind of like hiding some stuff here. A lot of the content that I'll be using for this lecture, as well as some of the rest of the lectures this week, came from this really great blog post by Lillian Wang about reinforcement learning. It is a very good review, so if you want to have something to kind of just refer to and see all the little differences between everything we talk about, this is a really great blog to just kind of print out and sort of refer to periodically. I'll also be referring to a couple of lectures from a Stanford class called 234, which is about reinforcement learning. So if you're interested in reinforcement learning at depth, I highly recommend checking out Stanford 234 because it's an entire semester course or quarter course, whatever they do, specifically on these subjects, and go into depth on this and everything else that I'll be talking about. So highly recommend that. So, okay. One of the first things that we can talk about is like, can we, given a particular policy, can we evaluate the value function given that policy, right? So let's start off with this kind of statement up here, which kind of expresses our situation, right? The value of our next time step given a particular policy is going to be the expected return, like a reward signal we're going to get for that particular next step that we take, plus this discount factor times the value of that next state that we see. So we take an action under our policy, or pi a given s, right? And then we are given a new state. And so that's kind of the right side of this equation here over all possible actions. So remember, we may have a stochastic policy, but in the case that we don't, we only deal with the one action that we take. So this just becomes 1 because the likelihood of that particular action is going to be 1. And then we multiply that by all of the different transition probabilities plus the reward we would see in that given state plus the discount factor multiplied by the value of that new state. So that's all this sort of expectation resolves into. And if we just do this over and over again, then we essentially have evaluated our policy. And again, this depends. All of this dynamic programming stuff depends on the fact that we know our probability distribution of our transition probability. So you might be saying, well, how do I even use this? Well, many times you can't because you don't know. This is assuming that you have an MDP and you know all of the different transition probabilities, in that system. And so we can also do this by way of the Q function, the state action function, right? And what we're doing here is we're now taking the expected reward of that reward of the next time step plus the value given that, and because we don't need to deal with the action because we're looking at a particular action, we drop this distribution on the front, and so you can kind of see that the value of an action and state pair simply is this sort of probability distribution plus times the reward we're going to get at that step plus the value function, the value of that next state. This is what's called on policy, where, well, sorry, hold on, let me pause because I always screw this up. Okay, sorry, I'm glad I looked that up really quickly because I kind of screwed this up. In general, with RL, you've got a variety of different types of algorithms. You're either model-based or you're not model-based, or you're on policy or off policy. But when you're model-based, you actually don't really talk about a policy. In fact, what you're doing is you're evaluating a particular policy, given that this is the value function under a given policy, or a state action function under a given policy, and then you actually compute a new policy based on that. So I'm looking at all of the different states, and then given our values of Q or V, right, I can basically say our new policy is going to be based on these updated values, the one that maximizes the Q value for every particular state that I might be in. So in that case, we actually don't really have a policy so much as we do a policy defined by our value function, and also by our state action function, depending on which strategy you're taking. And so actually this kind of brings me to almost the last slide of this, right? The way that all of these algorithms kind of work is what's called policy iteration. So what we do is we start off, we have a pi naught, or our kind of initial policy, which is generally determined by just the value function that we have. We evaluate that policy, which we do by way of this sort of policy evaluation. We then arrive at a new value estimate, and then based on that, we come up with a new policy, because now our value function says, right, we're actually defining, like you can see, our policy is defined explicitly by the value function. So it's a little bit kind of confusing because there is no policy, there is no like function to which I give a state and it gives me back some kind of distribution or something like that. In fact, the policy in these cases, in the context of dynamic programming, are defined explicitly by the value function or by the state action function. And so, what you're doing here is you're actually, okay, and this is, I think, another sort of gotcha that often goes doesn't make sense. These are functions that are algorithms that are constantly, you're iterating, and you're gonna sort of stick this value function in. It's going to be randomly initialized, and you're going to start to iterate, and over time it's actually going to contract and converge down into the optimal value function. I think it's a little bit out of the scope of this course to talk about that, but if that's interesting to you of why the Bellman backup converges to that, it's because the Bellman backup is a contraction operator, meaning it's proven to converge. And if you're interested in the proof, I really recommend checking out this lecture, CS234. It's on YouTube for free. Check it out. And they do a great job of explaining how the Bellman backup essentially contracts and guarantees that at convergence you get a optimal policy. If again, and this is, I'm going to stress this a million times because it's like the reason none of these things are actually used in practice. This is based on whether you know the model. If you know the transition probabilities. If you don't know the model transition probabilities, good luck with this. This won't work. So just to kind of go through, the value iteration process, right? This is the literal algorithm here. So you start off with k equals 1. You initialize your value function to 0 for all states, and now you do this until a convergence. And convergence is defined by the change in your value function being essentially very small. Let me move myself over here. So now we start for every state. We calculate the value of the next time step of this iterative process as being the maximum reward given a state and action pair, plus this discount factor times all of the different likelihoods of going into another state. So you can kind of visualize this as a tree, right? And you're just like, okay, I'm here, and if I go here and here and here, and these are the likelihoods of going to each one of those, I'm going to sum those and take the expected value times the discount factor. And so you can really sort of just see this as a Bellman backup operator on your V function. So the operator here is designated by B on VK. And so now your policy is explicitly dictated by this maximum, as shown below. So that's kind of it. So yeah, just to recap, right, with value iteration, we're operating directly on the value function or the state action pair. The iteration of, this is actually, I think, a good point to bring up too, right? Policy iteration requires an infinite horizon case, and it actually does not operate on a policy at all. It actually helps you determine a new policy, versus you're just sort of searching the space of possible policies. And in both of these operations, like the policy iteration or value iteration, what have you, does really require you to have this knowledge of the world. So yeah, that's kind of it. That's kind of it for dynamic programming. It really just comes down to this equation, this process. there's not too much to it, but it's not used very often because you need to know the world model, and very often we don't have a world model. A recent big area of research is world-based reinforcement learning, but the world is a learned model. We're approximating the world, and then we can do things like this on our learned model, which is really cool. And we may talk about that in a future set of lectures versus this one. But that's it for dynamic programming RL approaches. And next, we're going to talk about Monte Carlo reinforcement learning approaches, which are used when you don't know the world model. So it'll be our first model-free reinforcement learning approach. So